Smelly stat, how are they training you? I hope they're using StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about how to prune regression trees. There are several methods for pruning regression trees. The one we'll talk about in this quest is called Cost Complexity Pruning, aka Weakest Link Pruning. We'll start by giving a general overview of how cost complexity pruning works, and then we'll describe how it's used to build regression trees. Note, this StatQuest assumes that you are already familiar with regression trees. If not, check out the quest. The link is in the description below. Also note, this StatQuest assumes that you are already familiar with cross-validation. If not, check out the quest. In the StatQuest on regression trees, we had this data. Given different drug dosages on the x-axis, we measured the drug effectiveness on the y-axis. When the drug dosage was too low or too high, the drug was not effective. Medium dosages were very effective, and moderately high dosages were moderately effective. We then fit a regression tree to the data, and each leaf corresponded to the average drug effectiveness from a different cluster of observations. This tree does a pretty good job reflecting the training data, because each leaf represents a value that is close to the data. However, what if these red circles were testing data? These three observations are pretty close to the predicted values. So their residuals, the difference between the observed and predicted values, are not very large. Similarly, the residuals for these observations in the testing data are relatively small. However, the residuals for these observations are larger than before. And the residuals for these observations are much larger. These four observations from the training data with 100% drug effectiveness now look a little bit like outliers. And that means that we overfit the regression tree to the training data. One way to prevent overfitting a regression tree to the training data is to remove some of the leaves, and replace the split with a leaf that is the average of a larger number of observations. Now, all of the observations between 14.5 and 29 go to the leaf on the far right. The large residuals tell us that the new tree doesn't fit the training data as well as before. But the new subtree does a much better job with the testing data. Thus, the main idea behind pruning a regression tree is to prevent overfitting the training data so that the tree will do a better job with the testing data. Bam! Note, if we wanted to prune the tree more, we could remove these two leaves and replace the split with a leaf that is the average of a larger number of observations. And we could then remove these two leaves and replace the split with a leaf that is the average of all of the observations. So the question is, how do we decide which tree to use? In this StatQuest, we will answer that question with cost complexity pruning. The first step in cost complexity pruning is to calculate the sum of the squared residuals for each tree. In this example, we'll start with the original full-sized tree. Here is the original full-sized tree. The sum of the squared residuals for the observations with dosages less than 14.5 is 320.8. So we'll save that sum of squared residuals underneath the corresponding leaf. The sum of squared residuals for observations with dosages greater than or equal to 29 is 75. The sum of squared residuals for observations with dosages greater than or equal to 23 and less than 29 is 148.8. And the sum of squared residuals for observations with dosages greater than or equal to 14.5 and less than 23.5 is 0. Thus, the total sum of squared residuals for the whole tree is 320 plus 75 plus 148.8 plus 0 equals 543.8. So let's put SSR equals 543.8 on top of the original full-sized tree. Now let's calculate the sum of squared residuals for the subtree with one fewer leaf. Going back to the data, the sum of squared residuals for when dosage is less than 14.5 is the same as before. And it's the same for when dosage is greater than or equal to 29. But we have to calculate a new sum of squared residuals for when the dosage is between 14.5 and 29. Thus, the total sum of squared residuals for this tree is 320 plus 75 plus 5,099.8, which equals 5,494.8. So let's put SSR equals 5,494.8 on top of the subtree with 3 leaves. Similarly, the sum of squared residuals for the subtree with 2 leaves is 19,243.7. So we put SSR equals 19,243.7 on top of the subtree with 2 leaves. Lastly, the sum of squared residuals for the subtree with only 1 leaf is 28,897.2. So let's put SSR equals 28,897.2 on top of the subtree with 1 leaf. Note, the sum of squared residuals is relatively small for the original, full-sized tree, but each time we remove a leaf, the sum of squared residuals gets larger and larger. However, we knew that was going to happen because the whole idea was for the pruned trees to not fit the training data as well as the full-sized tree. So how do we compare these trees? Weakest link pruning works by calculating a tree score that is based on the sum of squared residuals for the tree or subtree, and a tree complexity penalty that is a function of the number of leaves or terminal nodes in the tree or subtree. The tree complexity penalty compensates for the difference in the number of leaves. Note, alpha is a tuning parameter that we find using cross-validation, and we'll talk more about it in a bit. For now, let's let alpha equal 10,000. Now let's calculate the tree score for each tree. The tree score for the original full-sized tree is the total SSR for the tree, which is 543.8, plus 10,000 times t, the total number of leaves, which is 4. So the tree score for the original full-size tree is 40,543.8. Now let's save the tree score below the tree and calculate the tree score for the subtree with 1 fewer leaf. The sum of squared residuals for this subtree is 5,494.8. And since there are 3 leaves, t equals 3, and the total tree score equals 35,494.8. The tree score for the subtree with 2 leaves is 39,243.7. Lastly, the tree score for the subtree with only 1 leaf is 38,897.2. 0.2. Note, because alpha equals 10,000, the tree complexity penalty for the tree with one leaf was 10,000, and the tree complexity penalty for the tree with two leaves was 20,000, and the tree complexity penalty for the tree with three leaves was 30,000, and the tree complexity penalty for the original full-size tree with four leaves was 40,000. Thus, the more leaves, the larger the penalty. Now that we have calculated tree scores for all of the trees, we pick this subtree because it has the lowest tree score. Double bam! Note, if we set alpha equals 22,000 and calculate the tree scores, beep boop, then we would use the subtree with only one leaf because it has the lowest tree score. Thus, the value for alpha makes a difference in our choice of subtree. So let's talk about how to build a pruned regression tree and how to find the best value for alpha. First, using all of the data, build a full-sized regression tree. Note, this full-size tree is different than before because it was fit to all of the data, not just the training data. Also note, this full-size tree has the lowest tree score when alpha equals 0. This is because when alpha equals 0, the tree complexity penalty becomes 0. And the tree score is just the sum of the squared residuals, and, as we saw earlier, all of the subtrees will have larger sum of squared residuals. So let's put alpha equals 0 here to remind us that this tree has the lowest tree score when alpha equals 0. Now we will increase alpha until pruning leaves will give us a lower tree score. In this case, when alpha equals 10,000, we'll get a lower tree score if we remove these leaves and use this subtree. Now we increase alpha again until pruning leaves will give us a lower tree score. In this case, when alpha equals 15,000, we will get a lower tree score if we remove these leaves and use this subtree instead. And when alpha equals 22,000, we will get a lower tree score if we remove these leaves and use this subtree instead. In the end, different values for alpha give us a sequence of trees from full-sized to just a leaf. Now go back to the full dataset and divide it into training and testing datasets. And just using the training data, use the alpha values we found before to build a full tree and a sequence of subtrees that minimize the tree score. In other words, when alpha equals 0, we build a full-size tree since it will have the lowest tree score. However, when alpha equals 10,000, we will get a lower tree score if we prune these leaves and use this tree instead. And when alpha equals 15,000, we will get a lower tree score if we prune these leaves and use this tree instead. Lastly, when alpha equals 22,000, we will get a lower tree score if we prune these two leaves and use this tree instead. Now calculate the sum of squared residuals for each new tree using only the testing data. In this case, the tree with alpha equals 10,000 had the smallest sum of squared residuals for the testing data. Now we go back and create new training data and new testing data. And just using the new training data, build a new sequence of trees from full-sized to a leaf using the alpha values we found before. Then we calculate the sum of squared residuals using the new testing data. This time, the tree with alpha equals 0 had the lowest sum of squared residuals. Now, we just keep repeating until we have done tenfold cross-validation, and the value for alpha that, on average, gave us the lowest sum of squared residuals with the testing data is the final value for alpha. In this case, the optimal trees built with alpha equals 10,000 had, on average, the lowest sum of squared residuals. So alpha equals 10,000 is our final value. Lastly, we go back to the original trees and subtrees made from the full data and pick the tree that corresponds to the value for alpha that we selected. This subtree will be the final pruned tree. Triple bam! Hooray! We've made it to the end of another exciting StatQuest. If you like this StatQuest and want to see more, please subscribe. And if you want to support StatQuest, consider contributing to my Patreon campaign, becoming a channel member, buying one or two of my original songs or a t-shirt or a hoodie, or just donate. The links are in the description below. Alright, until next time, quest on!